Okay, so I welcome you all to this week 8 doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor N.P. Padi and Professor Premlata Jina from IIT Roorkee. I am Swastik Sharma and I am a TA for this course. Since the beginning, we have been studying about various changes that are occurring in the system and how the grids have now become more smart, or they have started becoming smarter because of the fact that the conventional ways on in which the power used to get transmitted to us has now changed. We now have renewable energy sources, and we now have distributed energy resources as well, which are coming up at the distribution side. So earlier, the distribution systems, they were passive, and now what they have become active in nature, right? Now, from all the things that we have learned till week 7, even week 8, now what we'll start to observe is how in real world application they are being, how are they being used or utilized in a real world application or a real world scenario, right? Because in real world, management of these resources is sometimes tricky, and and you need to be able to we'll start with the optimal PMU placement, and we'll see that even though PMUs, they guarantee phasor estimates at each and every bus that they are connected to, but because we have to optimize cost, right, we cannot use PMUs at all buses. It's not economical. We'll see how in real world scenarios, how practically we are extracting or how practically we are managing these resources which enable a more smarter grid. And we'll discuss about demand response and demand side management as well to the end of this lecture. Let me show my screen. Okay. Okay, so we'll just give me a moment. Okay. Okay, so the first thing that we'll see today is the how the PMUs and how do we find the optimal places or optimal buses at which we shall connect a PMU, right? PMUs are costlier devices, even though what they do is they provide us phasor estimates for each and every bus that they are connected to, so that we can have an oversight on all our resources sitting at a very remote location as well, right? So these PMUs have to be installed in such a way that they can guarantee optimal utilization of their resources, right? They are a costly affair, and we cannot be connecting them at all places. So we'll see first a method in which how do we determine the optimal placement of this PMUs, right? So I've told you earlier as well, right? PMUs are nothing but phasor measurement units. These are phasor measurement units. And their usage is to provide phasors and measurements of phasors related to voltage or current to the dispatcher or to the controller, central controller, who overlooks the performance of the entire system, right? Now, their installation is limited by economic and infrastructural constraints, and we need to identify critical points or critical buses, or some generator buses or tie lines at which we should prioritize attaching these PMUs to, so as to have a closer monitoring. So critical buses, so what I mean by critical buses is the bus is more prone to violations or more prone to uh, or that can have a better oversight for the entire thing. So, as I told you, PMUs are costly, so we need to identify the optimal bus locations, and so as to we can reduce the overall installation cost, right? Now, in order to develop a model, so instructors and his students, they worked on devising this model, in which what they do is, so we have network data, right? Just a second. Let me see if it's recording. Yeah. Mm. So where was I? Yes. So the instructor, he developed a model with a student in which they are able to identify this the buses to which the PMUs would guarantee a better oversight of the entire network. So for that, we have our network data. So network data is freely available to us. All of the network that we have connected to the system, we can easily get the data, the network data of that system, right? So what uh, just a second. Yeah. So where was I? Yes. So what we want to do is we will first run a base case DCOPF. So DCOPF is also called as direct current approximation OPF. So one thing I want to make clear from this is that even though the name suggests that it's direct current approximation, it's just that the we take the assumption that the network is linear in nature, right? So when I say direct current approximation, it's not like it's applicable to direct current networks. No, it's applicable only to AC networks, but the approximation is called as direct current approximation. I'll tell you. Let me just give you the whole picture of what exactly this is, right? So since it's an optimal problem formulation, right? OPF means optimal power flow. So in this optimal power flow, what we do is we have to minimize cost, right? So we minimize cost, uh, right? So what we're trying to do is we are trying to minimize the cost of procure or running the generator at PG, right? So we are minimizing the total cost of running the generators to meet a specific demand, right? So the first constraint for any OPF problem is the power balance constraint. So we always write subject to when we talk about constraints. So we write subject to. So the first constraint is power balance constraint. In this, since it's a direct current approximation, what we do is we say that any net injection for a generator connected to any bus and for a demand at any bus, I is the index of the bus, is equal to the power flowing in the line that it is connected to, right? So we denote it by J, where we call it J such that I and J are connected. They are connected to each other. And what we have is we have only angles coming into picture. So this is the power balance constraint of the this uh, DCOPF, and it's run for all I in buses. Second thing is, since we are mapping it with respect to our with this generation. So what this exactly is, this is nothing but power flowing in a line I to G. So in a line connected between I and J, so this is the power that flows in it, right? So we have to limit this power. So every transmission line has a thermal limit, and this thermal limit is given by minus Pij max should be less than or equal to theta I minus theta j times Bij should be less than or equal to Pij max for all Ij. So this is flow limit, right? So what we are doing is we are saying that if there is a transmission line, irrespective of power flowing from left to right or right to left, the power flow is limited. It cannot go beyond PF maximum, right? So that is what this constraint tells about. Next we have generation limit constraints. Each generator can only generate between limits, right? So that limit is given by Pg min should be less than or equal to Pg is less than or equal to Pg max. This is for all G. So this is a simple DCOPF, a direct current approximation of optimal power flow, right? So we, as you can see, we have taken a lot of assumptions in this, and let's list out these assumptions. So the assumptions that we take are, so first we assume a flat voltage profile. Since we are not calculating voltage, we call that all the buses have VI equals to 1 per unit. So the voltage at all buses are same, and it's equal to the rated voltage of the bus. Second assumption that we have is that it's linear. So if you know from the linear approximation, right, all the equations are linear in nature. There is no non-linear term present, and you know from the Newton-Raphson load flow, or any load flow apart from the linear equivalent of them. Newton-Raphson load flow, if you know, these are they are transcendental equation. They have sine theta and cos theta terms, and they have multiplication of voltages with the and they have multiplication of voltages at two buses, right? So it's a non-linear equation. And what we do here right now is, it's a linear equation. We do approximation, and first approximation that we do is, we assume that there is no resistance, only reactance. So where does this come from? This comes from the fact that R by X is very low. So we assume that resistance is 0, and there is only reactance present in the system. Fourth, we assume that there is no active power. There is only reactive power flowing in the system. Sorry, there is no reactive power. There is only active power flowing in the system, right? So we assume only active power, no reactive power. And you can see, right, the voltage profile is flat. It's all 1 per unit, right? So if there had been some reactive power in the system, the voltage profile would not have been flat. It would have been varying. So these are some approximations that we do. And if you do the same approximation to your to the line flow of your Newton-Raphson load flow, you will get the same. Um, uh, so your the the equation that you'll get will match this equation. So what we do is, from AC power flow, we are just getting DC power flow. When we say DC, it means it's a direct current approximation where we assume that everything is linear, there is no non-linear term present, right? So this is what a short introduction to DCOPF. I did not want to go in depth because instructor has already covered, and it's very basic. I mean, you all know pretty well. So this is where so this is the DCOPF, what we do, and what we get from DCOPF is, the output is your voltage angles and your generation values, PG values, right? So what you get from DCOPF is that what are your voltage angles going to be at all buses. Voltage is the magnitude are 1 per unit, right? So what you're concerned with is only the angles of the system, right? So voltage angles you will get. And the second thing you will get is your PG values, the generation of your individual generators. So PG from individual generator that you'll get from this. So these are called true results. So what you get from the DCOPF is your true result, because these are now being scheduled into the system. Right. Now what you want to do is, you want to optimize the cost. And by optimizing the cost, what you do is, you take two more constraints and you formulate one more uh, um, optimal problem. And that is, you minimize this time the cost of the PMU with respect to the state estimation constraint as well as the observability constraints. Let me tell you how. So this is the objective function. The objective function. So this is, sorry, I won't go in this. This is DCOPF only. So this I've covered. The second objective that you have to follow is, you have to minimize the placement of individual PMU. So CPMU is what? This is cost of a PMU, and each PMU is mapped with a binary variable xi. This xi denotes one if a PMU is connected to a particular bus I, and it denotes 0 if it is not connected to any bus I, right? And then you have state estimation constraints. So why do we require state estimation constraints? Is because the fact that the PMUs, they have internal errors, right? And if you don't account for these errors, the problem, the placement or the numbers that you will get from the from this solving this objective function or this minimization problem is it won't be correct, right? Because it's not taking the fact that PMUs may give erroneous results, right? So what you do, you quantify the error, you quantify each error from the PMU, and based on that, you displace that in such a way that you calculate the amount of error that you are getting from the system, right? By using the true values. And using that, you write this equation that if there is a generator connected to a bus I, its minimum maximum limits are given by these equations, right? And the similar thing is done with demand, considering that demand is controllable. That's it. So this PD here is considered to be controllable. When I formulated it over here, I just assume that PD is not controllable. You can always control PD if you can control. But yeah, so yeah, they do this for PD as well. And what they the second constraint is that the voltage angle is between minus 90 and 90 degrees in radians, right? That is what they did. And the second thing is that any error coming from measuring the voltage angle is between this error term, right? So the estimated error versus the true value, sorry, the estimated voltage angle versus the true value is less than or equal to the error of the PMU in both sides, since delta can go in negative as well. So that is why they have taken a negative constraint over here as well. So this is the state estimation constraints that they have employed. Next constraint they have taken is observability constraint. What do they mean by this observability constraint? If you take a look at this, they say that the sum of xi's, the total xi's, if you add them together, they should be greater than equal to 1. What does that mean is that there should be at least one PMU placed, right? And why are they doing it? If you take a look at this objective function, we are trying to minimize cost, right? What is this? You want to minimize cost. So one thing to do if you want to minimize cost is just keep xi 0. Xi is 0 for everything, right? If xi is 0, the cost is 0. As soon as the xi becomes 1, there is some PMU that will get installed and there will be a cost associated with it, right? So as to escape that, so as to escape the fact that if you don't add this observability constraint, what will happen? Your objective, sorry, this problem will give you the results of this problem will be that xi should be 0, because that ensures that all the don't place PMUs at all. You will have no cost. That is intuitive, right? But you know that you need to place a PMU because you want to get observability out of it. That is why you add this constraint. So, and one more thing, this ensures that is that it will cover the neighboring bus as well. So let's say that you have two bus system, right? If you connect PMU at bus 1, you can easily calculate bus 2 values as well by just doing Kirchhoff's law, or, Kirchhoff's laws or Ohm's law, by using Kirchhoff's and Ohm's law, right? Based on that, you can easily calculate the associated values of bus 2. So you don't need to place a PMU over there. So that is what that is something that it can cover too. So based on this problem optimization, so they ran it for an IEEE 30 bus system. So I'll just run it over here. So ran it for IEEE 30 bus system, and they found out that the optimal number of PMUs is 7. So, and this is verified. This is verified from an earlier paper. If you go and take a look at the paper that is over there in the sir's um, uh, lecture notes, you'll see that he has given the link to the reference to that paper, and you'll see that the optimal number comes out to be 7 only. So this is how you can, given the fact that the PMUs are very, the PMUs are, a very costly affair. Connecting them at all buses is not feasible. So to ensure that you can get a corresponding optimal amount of the numbers to be PMUs to be placed at, you can get it by running this optimal PMU placement model. Right, so that is what was discussed in the first lecture. And next, moving on. So PMUs, what they do is they are devices that are communicating with your operator, or another device is connected in vicinity to it, right? So what they're doing is they are connecting, they are measuring, and they are conveying that measurements to a to uh, some phasor data concentrator, or directly to the central controller, right? Now, uh, this type of system in which you have a physical layer in a way that the components are tangible. Like for example, your generators, your transmission network, everything corresponds to a physical layer. And we have added now a cyber layer to it. A cyber layer is the communication that is happening and the data transfer that is happening between devices, right? So the smart grids had introduced a new kind of system. So they have created they have converted a physical system to a cyber physical system. So I'll just write smart grid. So smart grids are cyber physical systems because they have a physical layer. They have these transmission networks, their generators, and everything. So I'll just mute you. Yeah. So 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 smart grids are essentially a cyber physical system because they have a physical layer in which we have transmission networks and all, and a cyber layer in which communication and data exchange is happening, right? So this is a pictorial representation of what I just said. So you have physical entities, your generation, transmission network, distribution, and consumption, and the information flow happens between a communication network. This communication network corresponds to your cyber layer, which is then connected to your energy management systems, your SCADA, or your AGC, or any load frequency control that's happening, right? So I'll just write it over here so that everyone is on same page. So cyber, it's nothing but communication layer at which data exchange happens, right? And your physical layer is nothing but right. So this is what a cyber physical system is. So there are some benefits to it. So a cyber physical system is, it enables flow of data exchange, right? So it enables data exchange via communication, right? So because we have a cyber layer in which data can be shared, we have an data exchange via communication network, right? This helps us in two-way flow of information, right? And this two-way flow is not only limited to information, it also gets extended to the energy flow as well, right? So since you are communicating, you can communicate the flow of energy too. Next, because your devices are not communicating with each other, they are communicating with the controller. They have a centralized facility in which the measurements can be processed. They help in maintaining a safer and uh, a safer and a secure operation of the grid. Right? So since you are communicating, you help in managing this. Next, what you have is you can have automated and autonomous control. So since they can now communicate, you can automate anything, and that is why you can have now automated or autonomous control. But with this comes a few drawbacks as well. So since you have another layer, so this layer can be used by some kind of a some form of cyber attack, right? If someone can penetrate this layer in such a way that they can manipulate the data exchange, what they can do is they can indirectly have a cyber attack kind of a they can attack this layer so that they can create an imbalance in your system. So prone to cyber attacks. So I have forgotten the exact year, but you can go ahead and check. So one form of cyber attack happened on this Ukraine grid. I don't know by which country, but in Ukraine there was some form of a cyber attack in which their grid was completely shut down, or it was going to get shut down. I don't remember the whole situation, but yeah, I remember that some form of cyber attack took place over there, right? Second, there can be communication latencies or communication delays since they rely on communication, right? So there can be some form of delay, something happened and your communication didn't reach at the time in which the decision was to be made. So that is also a drawback of the system. Next, since what happens is these data, how are they exchanges? They are exchanged in the form of packets. So what we call is we call these data as packets. So if some dropout happens, if the packets are not transferred, so you won't get the measurements. Like for example, if I'm talking about PMU, right? PMU transmits some data to the PDC, and let's say some dropout occurred, the packet dropout occurred. These measurements won't get transferred, right? So for that full time duration, you won't have the measurements available to you. So it's prone to packets dropout, right? N- Other thing that can happen is since they are being transmitted over a network, communication network, you can have some congestion or some jamming as well, right? And if that happens, your communication will get delayed. And the last drawback is the malicious. uh, Also, I've already written prone to cyber attacks, right? So you can have malicious intent as well, in which you can just attack a uh, cyber layer of the system, and then you can just, I mean, you can create an imbalance in the system. So how does this happen? How do these cyber attacks happen? Let's get a little, let's dive a little in this. So what happens is, let's say that you are Posoko, right? And what you did was you sent some signal to the system, and it was sent so as the system was, you were assuming that the system was behaving um, securely. Yeah, it was in a safe operation, right? It was operating within the standard limits, right? Let's say that you saw the voltage at a bus and it was between 240 to 240 volts, right? And it was between 0.9 to 1.1 per unit. But let's say some cyber attack happened, and what it did was it it injected the data that instead of reporting a 1 per unit value, he reported a 1.2 per unit value, right? Now this value 1.2 per unit value, this didn't happen. Your voltage at the particular bus that you are concerned with, it was within safe and standard limits, right? But as an attacker, I told you, I transmitted the data by manipulating the data that the bus voltage has gone above 1.1 per unit and it's now 1.2 per unit. You saw that, right? The system operator saw that it's 1.2 per unit. Now you started taking some safety actions, right? If you took take those actions for a safer operating for a grid that is operating safely, you what you do is you remove generation, or you increase the reactive power flow towards that bus, right? Now what happened, you did that, and now you what you found out was the voltage uh, s- eh, the voltage dipped, and as it dipped, because you were saying that it was at 1.2 per unit, so what you did was you took some reactive power from that bus, right? So you installed SVRs or anything, and now what you wanted to do was you wanted to bring 1.2 back to 1.1, between 0.9 and 1.1. Now your limit was already 1, right? So the bus was already operating at 1, but it was made to seem like it was at 1.2, and you took some actions. Now the bus voltage will fall. So these are some kind of attacks that happen. So what you're doing is you are changing the pattern of the data. pattern of the data in such a way that the system operator or the operator feels that something bad has happened which hasn't happened yet, and it it takes some measures to control that effect. And what happens is that the system goes into uh, so the system goes into an emergency mode which it wasn't supposed to be. So these are the attacks called as data manipulation attacks. So what you're doing is you are manipulating the data. The data was, it was 1 per unit, but you told it was 1.2 per unit. So this is what happens in these kind of attacks. So there are two kinds of data manipulation attacks. One is false data injection attack. That is the one that I just gave you an example of, in which you you add some false data, right? The other kind of attack is DOS, or denial of service attack. In denial of service, what you can do is you can insert yourself in such a way that you can uh, jam the network by sending a flood of requests, right? If How does congestion happen? It's a pipe, right? The communication is happening. Assume that the communication network is a pipe. So the pipe has a certain volume that it can flow. It can flow only a certain volume of water from it, right? Now what you're doing is you're sending a flood of requests, or you're sending too much water into the system. This pipe won't suffice, and what has happened now, this has become, the water now starts accumulating over here, so it's not getting passed from that network. So what you're doing is you're essentially denying the service that was meant to happen. So such kind of attacks, these are called as suspended communication attacks, in which you flood the request in such a way that communication network now becomes congested, and as it is congested, you are denying the service that it was meant to be. The other kind of denial of service attack is a man in the middle attack. So what happens in a man in the middle attack? So an attacker, it intercepts, or it can intercept or alter some data between two communication entities, right? So let's say you are system operator, you're communicating with a PMU at a remote location, right? Now you both are in direct communication with each other. So what you can do is you can have two kinds of attacks. One is a unidirectional attack. So in unidirectional, what happens is, so system operator is sitting here, the PMU is at the other end. So what is happening is system operator sends some control signal to the PMU, right? And now what you do is you intercept the signal. So this signal has not reached the PMU, and you continue doing that because because it's not operating as it should. So you start to increase more and more control signals to the PMU, right? And the man in the middle, what it does is, the attacker, it intercepts all of those signals. So this is one kind of attack. This kind of attack is very difficult to manage, because you don't know if the system is behaving because it's there's some kind of attack happening, or because there is some form of a communication protocol that has been broken between you and your PMU. So you don't know what has happened, right? So these are very hard to manage, because it can be like you can feel that your communication between the two devices is not happening because it's offline, but that is not the case. It's just that the attacker is intercepting everything. In a bidirectional attack, what you do is, whatever control signal you are getting from this, you don't pass it to the PMU, but you send a different signal. Let's say you wanted this, let's talk about relay. So you issued a command that to this relay that close the switch, and the switch was not closed, right? But you send this man in the middle, what it does, it sends the signal that the switch was closed. Now the system operator feels the switch is closed, but in actual it is not closed, and this causes imbalance in the system. It can be very fatal for the system as well, right? So these are bidirectional attacks in which you intercept communication between two entities. Earlier you were only doing it for the PMU or the relay, now you're doing it for both the system operator and the controller. So these are some kind of cyber attacks that happen in smart grids, and it's a very advantageous for us if we can mimic or provide some sense of, if we can mimic how these attacks happen, we can find a way to get rid of these facts, these attacks as well, right? So we come to a very important definition, which is cyber security and cyber resiliency. So let's talk about cyber security first. I don't know why I just didn't write it over here, but let's. So what is cybersecurity? Cybersecurity tells it's the ability to protect oneself from a cyber attack, right? What does an antivirus do? It protects your computer from any virus attack. Similarly, cybersecurity is some form of measures that you take to protect yourself from a cyber attack. Or I won't write oneself, protecting from suitable measures. So you protect yourself by and if you can protect yourself, you can avoid the attacks altogether, right? Cyber resiliency, what it tells us, let's say an attack has happened, right? Your security was breached and some attack has happened. Resiliency tells how quickly you can bounce back from this attack. So let's say the some form of cyber attack happened, and now what this resiliency measures is the amount of time you take to bounce back to the pre attack conditions, right? So that is what cyber resiliency is. So cyber security controls or protects yourself before an attack happens, and cyber resiliency tells how resilient you are. If some form of an attack happened, you bounce back to the safer operating conditions. Right. So these are two important measures in which you quantify how resilient you are and how secure you are compared to by protecting yourself from grids, right? Now, how do you do this? How do you identify if an attack has happened, right? I told you, right, how many different kinds of attack there are, but how can you identify if some attack has happened? So for that, what we have is anomaly detection algorithms. So what usually happens in an attack, as I just told, so first your system gets compromised. There is some attacker who gets hold of your system. What it can do is it can either uh, do an attack on the transmission side or at the distribution side, or both all at once as well. So what it can do is it can change the reference settings of your. This is one form of attack I'm discussing, that something that can happen. What the attacker can do is it can send reference settings for your prime mover and exciter in such a way that uh, it, it it is not supposed to behave, but it now behaves as if. By changing the reference setting, what you're doing, you're changing the output from your generators, right? So what it does is by indirectly by get hacking through your system, it is changing the reference settings. If it does that, your generation changes, your frequency will get imbalanced. And if frequency imbalance happens, your power system's performance gets affected. Similarly, from the demand side, how does it happen? Let's say that you are controlling some resources at your distribution side, right? At the distribution side, you issue some malicious demand side commands. Now you'll see a sudden drop of load. If suddenly some load drops, what happens? There is a frequency imbalance. And if frequency imbalance happens, your power system performance gets affected. So you see, based on how your attack happens, your system's performance is affected, and you see the pattern. So what you have to do is to detect an anomaly. If an anomaly has taken place in your system or not, you just continuously measure your system based on how you would supposed to think it should have behaved, right? So let's talk about how these anomaly detection schemes pan out. So there are two kinds of anomaly detection schemes. So one is centralized and the other is distributed. In centralized, what you have is you have a centralized global. So you have some global variables on which your system's performance depends, and based on these global variables, you check if the system is behaving correctly or not. Right. So the first way of detecting an anomaly is by doing state estimation. So when I say detect an anomaly, what I want to do is essentially is look for unusual patterns in data. Always remember, whenever an anomaly happens, there is always some kind of patterns that form in your data that you get from your devices, right? From your controllers or from your measurement devices, anything. So based on that, what you can do is you can uh, detect if a cyber attack has happened or not. So the first thing is state estimation. So what is state estimation? In state estimation, you constantly get the voltage magnitude and the phase angle of all the buses. So you continuously do that. You check by doing the state estimation if your system is behaving as it should, right? So based on the state estimation, what you do is you get the values measurements from your PMUs, and you also have a model of your own. Based on the current injection and model, how your system should have behaved, you have a benchmark model and you have measurements coming from the PMUs. You check both of them if they are matching or not. If they are not matching, that means that your system is compromised. The other uh, anomaly detection scheme is chi-square. So this is not chi-square, it's chi. It's written like this. So in chi-square, what you do is, so so this chi, so this is a very basic test that happens in statistical models, in which what you do is you continuously check the difference between your observed data and your estimated theoretical data, right? So what you do is you have uh, just a second, if I can just push it down, I can have more space, right? This is B and delta, right? So what chi-square do is, what you get the observed measurements, whatever measurements you were getting, so you create a data distribution out of that. Sorry. So what you're doing is you create an observation of your observed data, and you also have, just take it to the next page, that would be much better. So where was I? Yes. So what you do is it measures the difference between your observed data distribution and your estimated theoretical data distribution, right? So in all of those techniques, what you're doing is you're checking with respect with a reference model, with a benchmark model. You're checking if your system is behaving as it should, right? And you'll see that this chi-square, if the difference increases, this chi-square value will increase. And if this increases, what you see is that there is some discrepancy in your data and that some anomaly has happened. Next is your residual based model. In residual based model, what you do is in this also you create a benchmark model. You create a model of your system and predict the, so what you want to predict is how, for a benchmark or a reference model, how the system should have behaved, right? So you predict the behavior of the system and check with respect to the observed data or observed behavior. So what you do is you subtract the quantities that you are measuring, whatever you are doing. When I say behavior, it can be some form of measurement, something that is happening in your system, right? So you check with respect to both of these, and if there is some residual, and if this residual becomes more and more, that means some anomaly has happened, right? Next is your binary hypothesis. In binary hypothesis, what happens is, so what you do is you have to you create your observation. You classify your observations into two categories. So how do you classify them? One is H naught hypothesis, the other is H1 hypothesis. So the H naught hypothesis is called as null hypothesis. So when I say null hypothesis, it means the system is behaving as it should. right? And when I say H1 hypothesis, it means the system is anomalous, right? So what you do is you have some form of hypothesis in which you know if my measured value is less than this, that means it is in H0 and that is in H1 if the data has behaved differently, right? So you can create these two kind of hypotheses, either H0 or H1 based on your earlier historical data, right? Because in historical data you can have both, right? If the system was behaving naturally, your all of these measurements will go into H naught, and if some anomaly happened, there was some disturbance or some anomalous distribution, all of those measurements will go into H1. Now what you do is you check if your x is so you check if some x measured quantity is in H naught with a probability p0. So you check if it is in H1 or not, H naught or not. Same with H1. And based on that, what you can do is you can get these probabilities and whatever, and you can just create some form of a metric to classify if an anomaly has happened or not. So based on historical data, you have created two hypotheses in which you have in H naught you have the normal data which corresponds to the safer normal operation of the system, and in H1 you had anomaly, when an anomaly happened, how the data was behaving, and based on that you continuously check and get the values from that hypothesis, and based on that you can specify some metric to quantify if an anomaly has happened or not. In model free, what you do is you use artificial neural networks or machine learning to figure out if an anomaly has happened or not, in which you can have some machine learning models, like for example support vector machines or classification models, in which you can train them in such a way that they are able to detect anomalies. So this is centralized. Why I call them centralized is because they depend on global data, right? So this data is only available to a central operator because they are measurement data. So let's say if so there are other kinds of, so let's say you don't have this data available with you, right? So what you can do is you can have a distributed algorithms too, right? So the first thing is you can have the same centralized methods, but what you do is you approximate the data. So like for example, you can have some form of you can develop some model which is able to mimic a centralized model, but it is not directly a centralized model. And what you can do is based on these approximation, you can just label it as a centralized model, but it is not a centralized model. It is something that you have created on your own. the main the main technique is the singular value decomposition. In singular value decomposition, what you do is you decompose your data into different matrices, right? Let's say that you had an x measurement data, right? When I say measurement, it's not directly coming from sensors. You can have some state estimation algorithm which is giving you some measured data, and what you do is you create a matrix out of it by having the rows as times, and here the data that you want to check, right? So you created this matrix, and mind you, this matrix is very high dimensional. When I say high dimensional, it can have numerous rows, numerous columns, right? So since this is very high dimensional, to be able to check if some anomaly has happened or not, it's very difficult, right? Because you can't just see every value and just check, okay, I feel that something wrong has happened. No, that is not how you do it. So what you do is you decompose this matrix into three different matrices. So X is decomposed into U summation V T. So these U summation VT, what it does is this U and V matrix are nothing but these show how the measurements sorry so how these measurements relate across different times and sensors, right? So I won't talk about how this decomposition has happened. That is not something that I have to go through. If you are curious, you can check. It's very simple to detect how this decomposition has happened. But I'll just say what is the significance of each matrix, and so that all of us are on the same page, right? So UV, they show us how the measurements different sensors and time, right? So you can check if how the data that you have gotten based on your power, voltage, frequency, or anything, how this is behaving. So you don't have a centralized model, right, to check with respect to what, but you got some measurements. Now you can check if how the data is behaving, right? So UV shows you how the data is behaving with respect to the sensors. U shows us with respect to sensors. V shows us with respect to time. And summation, this summation operator signifies how this relation, how significant this relation is. So let's say that you are getting voltage, frequency, and power from three different sensors, right? Now the voltage, frequency, and power sensors, these can have autocorrelation features. When I say autocorrelation, if voltage increases, there could be a fact that power has increased, right? So to check this autocorrelation, this is given by U. And with respect to time, it is given by V. And epsilon tells you how significant each of these relations are. Right. So based on these three metrics, what you do is now, since you are getting measurements, measurements, what you can do is you can uh, if you know that in SVD what happens is that if there are too many if there is no characteristic pattern, right? If the pattern is similar to what how a normal distribution should behave, these U epsilon V will be low dimensional matrices. All of these will be very low dimension in nature. As soon as some anomaly has happened, these become the patterns become increasingly aggressive, and these patterns are then visible in this U epsilon and V U sigma V matrices, and you can just see because their dimensions increase, you can then notice that some anomaly has happened. So that is how the singular value decomposition helps you in identifying if an anomaly has happened or not. Next is observer-based method, in which you can have some fault detection and identification techniques. So all of these fault detection identification techniques you can identify. How do you identify? Is you check if you're getting the same values that you could have gotten if the fault has not been there, right? So similarly, if the measurement has not been compromised, you know how the measurement could have looked like, and based on that you can take decision. Mind you, you don't have the corresponding model to predict the value, but you know from reference that how that value should have behaved. So these are some distributed algorithms. So that is so these this in this way you can detect anomaly in your system. So the detection of anomaly is extremely important if you want to check if a cyber attack has happened or not. And cyber attacks are something which people fear, because these are going to be kind of like in some form of a world war took place, right? If a country goes war with another country, there will be cyber attacks in your power grids, so that your power grids they so they can induce a blackout in your power grid, and that can be a it can be a do or die. It can contribute to a do or die situation, in which you won't have the necessary power to empower your forces, or to get your uh, to to where was I? Yeah, so to fight that war. So you won't have the resources. Power is everything, Your electricity controls all the aspects of your a kind of like your war, right? So you require power to, if you want to fly off a jet, you need it to communicate with servers, and these servers, what they are running on power, right? Everything runs on power. So if you can compromise their power, you can win the war. So cyber attacks are going to be, increasingly aggressively used in the coming if some war happened between two countries. So their detection is very required. Right. So this is what I wanted to discuss. So for a cyber physical system that our smart grid is, detection of anomaly is very important, and by these methods we can detect anomaly. Moving on. So next, the instructor delved into, okay, something happened. Now you want to, some imbalance happened with respect to anomaly or not, or generation going off, or load changing, anything. there is some frequency imbalance. Now you want to control it. So how do you control this imbalance? That is being controlled using your ancillary services. So let's dive into that. So what earlier used to happen, sorry, just increase the spacing. Hmm. So what earlier used to happen, so you used to have these so fewer but larger power plants. So your nuclear, your coal, your hydro, everything, these were few in quantities, but they were very large. They were in megawatts, right? 900 megawatts, 1 gigawatt, 5.2 gigawatts. And all of this, the all of their control was controlled centrally by a centralized operator, mostly in national level, right? Then you had large power lines and pipelines through which you used to transmit this energy. And it was always top to bottom. So from generation, the power used to flow down to the distribution level. And your distribution was passive. It only used to pay for the electricity. It never, it only, when I say passive, it was only the consumer of electricity. But now with renewables, what have happened, there are many small power producers. So you can have 5 megawatt power, the solar power plant, or you can have a few hundred kilowatt power plant as well, right? So you have few small power plants at all the different places. So what has happened now? It has led to decentralized control. So now your centralized control is not feasible here. You need to have many decentralized people controlling this. So you see, POSOCO has RLDCs. So these RLDCs are decentralized. So each controls a specific region and they report to the NLDC or POSOCO. So then you have small scale transmission and regional supply compensation, right? So you have transmission network at your regional sides as well as national side. And now the power can flow from both directions. It can flow from distribution to transmission and transmission to distribution. And now the distribution has started becoming active in nature. It is actively producing power. It is no more a consumer of power, and it can participate in the system as well. So how is it happening? Because of introduction of electricity generating resources in the distribution side, your rooftop solar plants, your small scale wind turbines, everything that are now that are called distributed energy resources, they have come up at the distribution side, right? Which were historically assumed to contain only load. And how are they modeled? They are modeled using power electronic converters. These have this converters, right? AC to DC or DC to DC conversions. This converters has, what they have done is they have decreased the inertia on the system. So what is inertia? Going by the physical definition, inertia means if a moving body continues to be in movement for a certain period of time, even when the force has been withdrawn, right? Because of the inertia of the system. But power electronic converters, they don't have inertia. They behave very differently. Now, since they don't have inertia, what is happening is, yeah, so they have decreased the strength of the grid. And because these renewable energy resources, they are uncontrollable, you can't control the power output that much to that much extent. I mean, you can control by controlling the reference setting, but these are not that much controllable as much as your synchronous generators, right? And they are intermittent. At one point, your solar power plant is generating energy. As soon as the cloud cover comes, it stops generating any energy, right? So what is happening now is you have this renewable energy, renewable energy resources, which has decreased the inertia of the system. So increasing renewable energy penetration along with power electronic converters have reduced the inertia of the system. So this is a statement that I'm leaving you with, right? So what do I mean by inertia? Why am I so concerned with inertia, right? Let's talk about that. So you see, this is a case study in which what has happened is there is some, sorry, okay, some generation has capsized and you now have a generation loss, right? And if generation becomes less than load, what happens? Your frequency dips, right? Now, the lowest point to which this frequency dips is called as frequency nadir. This frequency nadir, lowest point to which frequency dips, right? Now what has happened is, uh, you know, to control the decay of this frequency, to control anything, you take some finite time, right? You may take 5 seconds, 10 seconds before, your automatic control kicks in, your control algorithms kick in. They take some finite time, right? To protect it from decaying further, what comes into play is the inertial response. What is inertial response? So let's say your rotating mass was rotating. It was rotating as earlier. Now some generation has gone down. What it should do is it should start spinning more, right? Sorry. Uh, when generation has reduced, what happens usually is your load becomes high, your frequency starts dipping. So what you need to do is you need to subsequently remove the load from the system as well, right? Now what happens is this generator, it starts to it's rotating on its own, right? It's rotating at that speed, and it continues to rotate because there is certain mass that it's rotating with. So the turbine which rotates, it has some mass, right? Some mass of this turbine is there, and when it's rotating, it continues rotating in that direction. Due to that, what happens is it arrests this frequency nadir. Otherwise, if that is not in there, in play, if inertial response is not in play, it will straight away go down, right? Which is bad. So what happens is, because inertia has reduced, F nadir, so F nadir and Rokov of the system has deteriorated. So what is Rokov? So Rokov is rate of change of frequency, right? So this is rate of change of slope gives you a rate of change of frequency. So based on this inertia, this hs is nothing but the inertia of the system. It controls the slope in such a way that it does not go beyond a certain value, right? And it kicks in immediately. So this inertial response does not take time. It kicks in sorry, my bad. It continues spinning, and it kicks in immediately, right? Within a few cycles. So this response comes into play within a few cycles. So this is called as inertial response. The system's inertia responds to the arresting frequency in such a way that it controls it. Right now, it has arrested that frequency nadir. It has arrested the Rokov from deteriorating further. Now, it is not sufficient. The inertial response in itself is not sufficient to, um, to arrest this dip. What it now does is it moves on to the primary frequency control. So the next response that comes is primary frequency control. In primary frequency control, what we do is we control it. It's first of all, it is also automatic. Even though it is automatic, I must say, even though it is automatic, it's not like it does not take time. It takes time. Control algorithms takes some finite amount of time, right? It's not like immediately like inertial response. So next comes primary frequency control, in which what you do is you control the governor or your droop control. So governor or droop control falls into this. So this group control we have discussed extensively last week. I hope you have all gone through it. So in group control, what we do is we control the characteristics of the curve so that it matches now the set point in such a way that frequency is at a nominal point. Let's say that this was not sufficient to control it, right? So next you move on to secondary frequency response. So you see your governor response, it increased this dip, but it decreased this dip or deviation, but it's not sufficient to come back to the normal operation range or the normal operation limit, right? Now what you do is you implement secondary frequency control. So I'm sorry, droop control won't fall into this, only governor control falls into this. My bad. In secondary frequency control, what you do is you control the automatic generation control or your droop control, right? So AGC falls into that. AGC is a control mechanism with the central operator which controls the output of your individual uh, power generating device, this generators in such a way that it can control in a fashion so that the frequency can be brought back to its normal level, right? So you see it has implemented it, but let's say it is not able to reach the perfect value. Now what you do is you can implement a tertiary frequency response as well. In tertiary frequency response, what you do is you from an ancillary services market, you procure frequency support. So you procure some kind of a frequency support from the ancillary services market. So what is ancillary? So I've been using this word. I thought everyone would know, but ancillary is support. Ancillary by definition means support. So ancillary services market means you can get some form of some form of tangible components from this market which can help you with the issues such as congestion, frequency drop, voltage imbalance, etc., etc., right? So this falls into the tertiary frequency response. So all of this happens so that your frequency is now back to its normal operating range. So this is what uh, this is a graph that I have gotten from internet. Uh, Sorry, which is for a specific case study in which um, this is from Grid India. POSOCO, when I say POSOCO, it's Power System Operator, but it's Grid India, I mean the grid controller of India. So this is their case study. In this, what happened was, you can see there was a very large generation loss. Around 4500 megawatts of generation was lost. So what happened? Your frequency, which was within the stable operating limits, started decreasing. And you know this this initial drop was reduced by your inertia of the system. So inertia decreased the frequency needed, right? So where was I? Yes. So within a few seconds, now what happened was your primary frequency response was kicked in. So you can see few seconds. It's written few seconds. I don't know why it's not there, right? So the primary frequency was and what it did was your governor output was controlled of and it continues for about 30 seconds. If the frequency is not brought back within 30 seconds, now they kick in secondary sorry I shouldn't say second, they now kick in the secondary frequency response. In this, what they do is they control the droop characteristics to bring it back to the stable operating point, right? And that is what they did. This continues for another 15 minutes and this frequency response kicks in 30 seconds. So you see there is a significant delay between how within the time at which the secondary frequency response was kicks in with to the time it was issued, right? And you see if it is still not within the certain band, you see if I withdraw this, if I continue this at this point, the system may not be back to 50 hertz, right? So what I do now, I initiate a tertiary frequency response in which I buy frequency support from the ancillary service markets. And you see it continues for another 60 minutes and now my frequency is back in the stable operating range. So this is what happens. And you have upper statutory limit and lower statutory limit in what if the frequency increases beyond this, your generators are tripped, and if frequency dips beyond this, your demand is disconnected. So you can have brownouts. So this is by ways in which your frequency is controlled in India. This is some case study that I got from the internet. Okay, so yeah. So one thing I want to discuss is, so as there is a frequency, system system deteriorates. So this is the maximum frequency dip, right? But now if let's say another thing happened, instead of your generation loss, your load was now lost. So now if the load becomes less, what happens? Your frequency starts increasing. So the point to which, if let's say the frequency increased, some load loss was happened, and if the frequency increased, this increase in frequency to the this is also a point at which, just like frequency nadir, there is a maximum point to which the frequency comes before it is controlled. So this maximum point is called frequency nadir. Sorry, frequency zenith. So this is maximum frequency rise. So in the case when generation becomes more, your frequency starts rising to the point frequency zenith before it is brought back to its safe operating limits. So, right now I told you, right, this is possible. So inertia is very important. Why? Because it arrests your Rokov, it arrests your nadir, so that it does not go beyond a point where it won't be manageable by the system operator, right? Just a second. Sorry. So yeah. So now you see inertia, why inertia is important. So so your synchronous generator, which had this much of stages in which your energy was stored in turbine in form of rotating mass, and your energy conversion happens in your synchronous generator. Now you require this inertia because, as I told you, it arrests the frequency nadir and controls the Rukov from deteriorating any further. And how is this possible with your power electronics based devices, right? For power electronics based devices which have no inertia, how can you implement this? So for that, what we have is we call virtual inertia, or we get some form of an ancillary support. And how do we get this virtual inertia? This virtual inertia you can get either from your energy storage device, this your energy storage device, let's say some form of your batteries. They can store power as well as give power back to the system, right? So they can store as well as produce. So based on this charge discharge, you can control in such a way that you can control the Rokoff or rate of change of frequency of your system. So your batteries can act like a virtual inertia or synthetic inertia. So if you see in this table tells you for different generating devices, what is can you get inertia or active power control out of it. And as you can see, for a conventional synchronous generator, because it has a rotating turbine, it has rotating mass, you have inertia in it, and you can also control active power by controlling the governor output, right? But your DFIG wind generator and your PMSG wind turbine generator, they are not directly connected across the grid. uh, if you know from this I don't have the okay, so I don't have a wind turbine diagram, but if you see from the wind turbine diagram, the rotor is connected across the grid by the help of a power electronic converter, right? It is not directly connected across the grid. Because synchronous generators, they are able to provide inertial response because they are connected directly across the grid and they sense the grid's frequency. But in this wind turbine generator, both DFIG or PMSG, permanent magnet synchronous generator, or your double fed induction generator, even though both have rotating mass, they both have rotor, they both have turbines, but because their rotor is connected through a power electronics based converter and the grid, it is not directly connected across it. It is not able to provide the inertia by means of that rotating mass. But still, by controlling the headroom, by controlling the amount of power it is converting or giving back to the grid, you can have some form of synthetic inertia from the system, right? And by controlling set points, you all know you can control active power. For PV array, there is no such arrangement. If you don't have a battery, you cannot have inertia, but you can control active power out of it because uh, you have the active power set points, right? By controlling the active power set points, you can control the active power output from PV array. Your battery storage, it acts like a synthetic. It has inertia. It has synthetic inertia. So there should be a there should be an asterisk over there as well. So they have synthetic inertia. They can store energy and give back energy power as and when they want. And demand response, this we'll study later. And you can see by controlling the demand, by controlling the load, you can also have some form of a virtual inertia into the system. So what, so let me give you a very, you know, a definition that you can, use. So what we do is manipulating. So what you do is you manipulate the control function in such a way that it behaves like a it has some inertia like a synchronous generator inertia. Right? So what you need is you need control mechanism like Rokoff control or frequency control to be able to get virtual inertia out of it. Right? So this is one form of a virtual synchronous generator in which you use control algorithms that power an inverter in such a way that you can get inertia out of it. Right. Now I said that demand response can also be right. You you can control generator. Fine. What if you control load? If you control load, you are also kind of like providing inertia to the system, right? So let's talk about how this demand side comes into play. So let's talk about first a few characteristics of the demand that we have in India, right? So in this first graph, you see we have peak demand. So you can see with each passing year, so this is for financial year, each financial year, you can see for each passing year, our peak demand has continuously increased. So the peak demand is increasing. But there is something that you need to check if you are able to meet that peak demand or not. Right? So let's start from 2015 to 16. You see, our peak demand was 156,871. So you had 1,56,871 megawatts of peak demand, and you were able to meet only 152.976 gigawatt out of it. Right? So you were not able to meet around 3 gigawatts of power, right? So you see that you have a deficit. Even though you have capacity to meet that load, you were not able to meet that load in 2015 to 2016. Let's come to 2024 to 2025. You have 249,856 megawatt of peak demand, and what you have from here is 249,854 megawatt of peak demand met, right? So for a peak demand of 249,856, you are not able to meet only 2 megawatt of peak demand, right? So you see we have come a long way. We have started to meet the peak demand which we were not able to do before, right? But what is happening is, even though you are able to meet peak demand, your distribution, they are continuously suffering. Why do they suffer? It's so I don't know if you know, but sorry. So I don't know if you know, but what is happening is the distribution discoms, they procure power at a varying rate. So it's not constant. Like for example, we get 2.5 rupees per kilowatt hour, right? Assuming, I'm just assuming, it's a flat retail price. Whatever we consume, how much ever we consume during any part of the day, we pay only one price, 2.5 rupees per kilowatt hour. It's an assumption, 2.5 rupees, right? But they are not procuring at 2.5, they are procuring at a higher value as well. I mean, based on how the price is changing, they can procure at more and pay at less, right? There's one more thing. The industrial consumers, they are cross subsidizing us. So what is happening is domestic, they cannot ask 5 rupees or 6 rupees to domestic. Like, and you see, political incentives are also now coming into play. Like they give free first 300 units. So someone is paying, right? For the 300 units, if the consumer is not going to pay, someone is going to pay. And that is coming down to the discom side. So discoms are increasingly under pressure in the form of losses. So you see, from 2015 to 2016, their losses decreased, but now since they have increased by a very big margin, right now they stand at around minus 80,000 crores of losses, 80,000 crores losses. So discoms are very much stressed. So they are not able to, if it continues happening without government support, they will not be able to sustain. So let's say if something happens, like for example in US, they don't have government support. The discoms they don't have. What they have to do is they have to somehow manage it, and they are running it profitably. Similar thing is happening in India as well. Sorry, in Australia as well. But you'll see that the prices of electricity is also more. That you cannot make it happen in India because of political incentives or anything that comes into play, right? So you cannot increase the prices of the electricity, but someone has to pay, and that someone is Discom, and they are under a lot of stress. And right, so because they are paying for the electricity, so to procure that electricity, they are paying more, but the revenue that they are getting from us is very less. So you see, agricultural loads, they are subsidized in the sense that industrial load or us, we cross subsidize them, so they get very cheap power, very cheap. But industrial loads, they don't get cheap power. So like for example, in IIT Kanpur, it's considered to be, an industrial load because it's very high, 15 megawatts we have a peak demand, right? For a 15 megawatt peak demand, we pay 7.5 rupees per kilowatt hour, and we pay a fixed cost too. So it's very high. So what we are doing is, because agricultural loads are not paying anything, we have to cross subsidize them so as to have a net zero for the for the discom. But that is not coming out to play as well. So if you see the category wise electricity sales mix, when I say sales mix, the sales means how much you are selling to the customers. So you see, at first, highest load is industrial, then comes domestic, then comes agricultural, then we have commercial loads, then public services, then others, and then our railway load. And electric vehicles are negligible right now. You don't see anyone buying electric vehicles, right? I don't have any electric vehicle. So, but if you see this graph, you can see that at one point of time, residential load was very high compared to industrial, but now industrial load has increased by a certain margin. Not by much, but still it is more than the residential load. So you see, this is how it is selling to different customers, and it is selling to these different customers at different prices. So it is not able to get back what how much amount it is paying to get that power from the grid, right? And for that, what it can do is it can induce some demand side management. So what does demand side management means? Altering, so I'll write it, altering or controlling customers demand. So since it's demand side management, what does demand side means? Controlling the customer's demand in such a way that their electrical consumption patterns can be controlled. Customers demand patterns. uh, so uh, th- uh, right, so you can control them in such a way to produce desired changes. The kind of changes you want into the system, you can control the or manipulate the demand of the customers. So how you can do is, there are few different ways. One thing to go by is peak clipping. In peak clipping, what you can do is, you see there is a peak happening here, and when peak happens na, just remember, if they are procuring it from market, if the load increases, the price of the generators will also increase, right? Because each generator has a different price at which it can generate electricity. Now if the load starts to increase, the generators that are able to supply electricity are also increasing, and it may so happen that now your electricity is coming from a generator that is producing at a higher value, right? Sorry, when I say higher value, it's coming from the generator uh, which is expensive. So if you see how market works, let me draw. So this is pi and p. So if your, let's say this is your generator curve, right? So let's say your, oh sorry, this is not your generator curve, my bad. This is your generator curve. So this is how your generator will generate electricity. With increasing power, the cost of producing that power increases. If your demand is less, if it is at this, the price you pay will be less. But if it increases to this point, the price you are paying is much. So pi 1 is greater than pi 0. So when peak happens, when there is a peak load in the system, the prices will also increase. But since we are getting flat retail price, it is very expensive for the generator to continue supplying it. Sorry, it is very expensive for the discom to continue providing electricity. So what it can do is it can clip that peak. By clipping that peak, what we mean by is we can curtail consumption of loads at that point. So what we can do is the demand side management, what it'll do is it will shut down loads of your system. So when peak happens, the loads will be shut down. So discoms used to have this cuts, so power cuts. So this power cut is essentially this only. At peak power, they'll have power cuts. So based on that, what happens is your peak is now clipped and it looks something like this. Or what you can do is you can increase the system so that it does not have a peak. So what you do is you increase the load by, these are valleys, right? You don't have much load in these curves. So what you do is increase the load so that it's something like this. Sorry, it's something like this. And if the load curve is like this, what will happen is you're procuring power from the expensive generator only, right? So you have an incentive to charge that much amount of money from your customers too. So that is something that you can do. Or what you can do is if the load is deferrable, let's say the load is not critical in nature and you can defer the consumption, or you can schedule the resources earlier as well. Like for example, your HVAC, start using it from 8 a.m. As soon as 2 p.m. comes, switch them off. Your rooms will be considerable cold so that they don't cause any peak on the system. So what you do is you shift this peak into these crests. So how does your load look? It looks something like this. So you see, peak has now been reduced by shifting the load to the points when the load was less. Or what you can do is you can conserve load. When I say conserve load, you can decrease the amount of load that is there in the system. So when you decrease, what you do is you decrease the peak as well. If peak is decreased, the price at which you will procure will also decrease. Or what you can do is you can increase the load altogether. So if the load was like this, increase it. So people don't generally do that. It is not profitable to do this, but it is some form of demand side management where you are altering the load so that it emulates as a growth load. So what I say flexible is that this load can be scheduled at any time. So flexible loads are those loads which are flexible with their power and energy needs, and you can schedule them at any time. So these are drawn with this dashed line, so show that you can control their loads in such a way that you can get this kind of demand curve from the system. Right, so this is called the demand side management. So what you're doing is you're altering or controlling the customer's demand patterns so as to bring about the desired changes into the system. Right. Hmm. So anything else I wanted to discuss, I forgot. Okay, so I have only this. Okay, so this is how you can do. Right now, so for this as well, so as to control which kind of load to trip or which kind of load to shift, you have to formulate another OPF problem, optimal power flow problem, right? So in this, what you do is you can have multiple objectives or a single objective. So you can have either a single objective function or a multiple objective. So always remember, so the demand side management is always induced by utility. Only the utility has the authority to control it, right? So in this single objective, what you can do is you can control the demand of the system in such a way that you have now a lower overall demand. So what you do is you minimize your actual demand minus the utility specified. So your objective function becomes something like this. So it can be either utility or user. So both can have some specific demand. You can write an objective function in such a way that you are trying to reduce this kind of a demand. So what you do is in single objective, you shift the flexible loads in such a way that the actual load curves becomes closer to the desired load curve, right? So what you do is you are minimizing how the actual demand looks like minus how you want it to look like. In multi-objective, there can be either utility specified, uh, you know, consumption patterns or your user specified consumption patterns, so that you can have actual demand minus 0.5 utility specified or minus 0.5 user specified, right? So you can control this objective function in this way. And there are some constraints as well. So these constraints, so what you want to do is you have flexible loads in the system. You are trying to control them in such a way that your overall demand on the system is reduced, right? So how do you do that? So these constraints are, you should have some finite controllable devices, right? So the number of, I'll write it with respect to, so number of controllable devices should be greater than or equal to 0, right? Second, number of devices to be shifted at time t, or yeah, devices to be shifted at time t. So these should be less than or equal to the number of devices available, right? So you cannot control more than, you cannot shift more than the devices that are present in the system, that are controllable in the system, right? At time t. So you have third, what do you want to do is, so you can only, so since it's a flexible load, right? So you cannot prepone their usage, because this constraint comes from the fact that you cannot, you cannot ask him to shift it. I mean, you cannot ask him to prepone it by coming it, asking him to do it before. You can always do it. You can postpone the usage of that load. So, yeah, so this DT should always be delayed, and this delay should be less than or equal to the maximum delay you can get. So let's say you want to go to a party, right? And you want to wear washed clothes, right? And you give the utility the control over your devices, and you are like, okay, but still I want to go to the party and I need considerable amount of time for them to be washed and then to be, dried, and so that you can wear them into that party. So what you can say is, okay, you can delay it, but make sure that they are done by 12, right? So you are setting the maximum number of hours in which that load can be deferred. So in this way, what you do is your flexible loads into this in the system, whatever loads that the utility can control, you are trying to control them in such a way that the peak demand is reduced, and that, and the all of the constraints are also met. So you can formulate this objective function in some mathematical, sorry, in mixed integer linear programming or mixed integer nonlinear programming. And what you can do is you can use mathematical solvers like mathematical optimization solvers or heuristic solvers to solve these objective functions. And that is what this case study also gives. So this is a case study in which what they do is, so for a commercial area and for an inertial area, they forecasted the load demand to look something like this, right? You see this demand, and what they say is, okay, I want to control it by decreasing the peak that is happening. So you see, there is a peak here and there is a peak here. So there's rapid increase and then rapid decrease. So control this. What you do is you run this system. You run this uh, problem formulation, and you see this is how your load looks. Yeah, sorry. This is how your load looks. So your load curve is now does not have that much of a peak, right? So you see it's something like this. So your peak, oh sorry, so your peak, if I do an average curve, right? Let's do an average curve. So your peak has now reduced. So that is what this objective function does. It tries to minimize your peak in the system. Similarly, if you see in this way, in this graph, you see there is an early peak. There is this peak. And what you do is you run this system, run this objective function formulation, and you get this peak now by controlling or deferring the load. So by using this, what you're trying to do is you're trying to mimic the peak of the system. So this is how DSM can be influenced into the system by formulating it as an optimization problem and solving that optimization problem. So one more thing that you can do is, so this is for multi-objective. So that was for a single objective. This is for multi-objective, in which you can see that you want to control it from both perspective, your utility as well as your user's perspective. And you'll see that earlier it was this, now it has become this. And then for industrial area, it was like this, and now it has become this. So this is how you can solve an optimization problem to control the peak of the system. Right. The next thing that the instructor of the course has suggested that you can have utility driven DSM using DC microgrid. So you can have utility driven DSM for DC microgrids. In this, what you do is essentially, since all of your renewable power resources, they are DC in nature, yeah, and your loads can also be DC. So with your AC microgrid, with your AC distribution system, you can have a DC microgrid in such a way that you can use that DC microgrid's ability to generate or produce power so as to contribute to that AC distribution system, so that it does not rely on that on the main grid. So you see, I won't go into detail. Please go through the lecture. I have explained one. This I feel that you should go and do it on your own. And you see the peak has now been reduced in both the levels. Right. So the main objective of this optimization problem was to reduce the peak of the system. Next, demand response. So this is one of the main DSM activities. What you want to do is you want the demand to respond in a way that it is able to react to the type of control signals you are specifying it, right? So as a controller, what you do as a utility, you can send in signals. Okay, I want you to reduce the power demand. So the demand can respond to that signal. It can either, okay, I'll respond to it, or it cannot respond to it. It's up to him. But in earlier utility demand side management, what we assumed was all the control was provided to the utility. Now the user has a say, and it can either contribute or not contribute based on the control signal. So the demand response is one of the main activities of DSM. So I don't know if you know, but the demand response is increasingly being adopted for the for Indian power grid, in which what we are trying to do is we ask, okay, if you have an AC, please run the AC at 24 degrees Celsius when there is peak power load in the system, right? And if you do that, we'll give you 100 rupees. So people do that. So there are distribution utilities which are doing that, which are incentivizing users to shift their usage or to control their usage in such a way that they can minimize the peak, and they compensate as well. They provide incentives to the users too. So the main aim that we want is we want to minimize the total energy electricity consumption. We want to reduce the amount of power generation required at a given time. We want to promote the idea of green and clean energy. So one main activity of demand response is, if you're trying to reduce your power, your power can be then met with your, renewable energy resources only. So you're in a way promoting clean and green energy as well. And since your consumption reduces, your generation reduces, your line overloading will also eliminate. So this is how a demand response process is done. In this, what we have is, there is an aggregator which is present at the distribution side. This aggregator is in contact with your independent system operator. An independent system operator operates the transmission system, right? And this ISO is in contact with your DSO as well as your aggregator, and your aggregator, also called as a demand response aggregator, is in contact with all of these different loads, right? And what it wants to do is, it can, based on the signals it gets from the ISO, let's say ISO experiences, okay, the peak is coming and I don't want the peak to come because I don't have energy. It will ask DSO to, okay, engage in demand response. Aggregator will engage in demand response, and your peak can be minimized. If your peak is minimized, what you are essentially doing is, you are providing inertia to the system. So now, inertia is different for different, your demand response is different for different types of resources, right? So your industrial resources, these are the high energy customers with a peak demand of a few megawatts. So these are high energy customers with a high peak demand, right? But since they are industrial, um, what they have some temporal dependency. When I say temporal dependency, they, let's say they have to produce some amount in some given day, right? So as to break even. So industry don't work like this. They have to create, or make certain amount of products in a day, so as to get the maximum benefit out of it, right? So as to maximize the profit. And you cannot control them indefinitely, right? So they can only, they need to be scheduled with a very high time precision. Precision, as they have critical temporal dependency. When I say temporal, it's varying with time, right? Next, we can have commercial. In commercial, they can be like some shops, right, or some mall. So these commercial, they can be made demand response ready by having energy efficient buildings, right? So the main load that they have is that of HVAC. HVAC is nothing but heating, ventilation, and air conditioning. So these HVAC loads can be controlled by the utility. The last on the strategy is residential. So these are you people living in your homes. You are residential customers, right? So what you can have is, you can have some home energy management system. So let's say that you are running your AC, run it at auto. If you run it at auto, what happens is, it can control the efficiency of the system in such a way that your temperature is maintained at the desired temperature level, and that the energy output is not too much. It shouldn't be like you are running your AC at 18 degrees Celsius and then taking a comforter or a blanket or a quilt, right? It defeats the purpose. So you can do one thing, you can run it at 25 degrees Celsius and take a bed sheet as a covering, right? Don't take blankets. Why do you want to take blankets, right? So that is what you can do. And the different kinds of load that we can have is, you can have some critical loads, right? So when I say critical, eat any induction cooktops or your cooktops, all of these are critical because you want to cook whenever you want, right? So these are critical. Then you can have thermostatically controlled loads, TCLs they are called. So your heating, ventilation, AC, all of these are TCLs. And then you can have some deferrable loads as well. Like for example, your washing machine or anything, right, which can be deferred. And these are measured these are measured based on these parametrics. The first one is quality of service. So quality of service measures the kind of if you are engaging in a demand response, what is the quality of that service that you are getting. Interoperability, what it measures is that it should be able to communicate with the utility, right? It should, and all of the devices, if a utility says, okay, switch off your device, you should be able to communicate to your device, okay, then switch off. So there should be interoperability. It should have scalability and flexibility, and it should be secure. So you see, if let's say that I have control over your loads and I can monitor your load consumption. So you see, if you live in a home, when you leave, the load becomes negligible or minimum, right? So if your load consumption data comes to a person who, who has malicious intent, it can take a look at your data and then gather, okay, when you are leaving and when you're coming back. Based on that, he can use it for, to make a robbery, or, to burgle the empire, to have, to rob your residential household, right? So that is, so it should be secure. Your data should not leak. So I would have loved discussing another form of demand response, but since it's not been discussed yet, I did not want to, delve into a topic in which you won't be interested. So yeah, so these are the few demand response programs. So these are based on control strategy, prices, or loads. In control strategy, what you do is you can either have a centralized control in which a utility takes control over all of your devices, or you can have decentralized control in which each of you can have a strategy, so that you control make the decision on your own. It can be based on price. I can give you prices, like for example, we'll discuss later. Yeah, I can either give you prices, or you can have incentive based prices. Like for example, I'll discuss dynamic price base in the next slide. In incentive based prices, what I can do is I can incentivize for your load consumption, right? Let's say I want you to decrease your AC to 20, sorry, increase your AC to 24. Why would I want to decrease it? Sorry. Increase your AC to 24, right? I can say, okay, at 2 p.m., please increase your AC to 24. I'll give you 100 rupees for that. So it's kind of like an incentive. Or I can penalize as well. So if you're not having all lighting loads as LEDs, so I can penalize because you're using a very, uh, you know, energy inefficient form of lighting, which is these CFLs, or, these 100-watt bulbs, which produce the same amount of light but take in a lot of electricity. So I can penalize you for that as well. Or you can have some based on load by scheduling the load, task related load, or energy related. By minimizing the energy, you can decrease the pattern of your load as well, right? So there are two different control strategies, in which there is a centralized control strategy where you have an aggregator which is in contact with each one of the households, and it is in then contact with your distribution substation. Or you can have a decentralized control strategy in which all of your residential loads can be in contact with each other, and as well as DR aggregator, which is in contact with your distribution substation. So this is decentralized control. And you can have dynamic prices based demand control, demand response. As I told you, I'll discuss it here. So in which you can have time of use pricing based on the time at which you're using a load. So let's say if you use the load at a time when there is not a peak happening in the system, I can charge less for it. But let's say if the peak is happening in the system, I can charge more. So it's called time of use pricing. In critical peak pricing, at critical hours when the price of the electricity is very high, I can charge more from from you. In peak load, it's same thing, but it's like critical peak can happen for a smaller peak as well. It can be, so this can happen for a smaller peak as well, for this as well, because even though the load is less for a particular for a particular distribution system, but it is procuring at a very high rate. So it is a critical peak price, and it will charge more for supplying power at that time. Then you can have peak load pricing. You know when peak will happen in your system, and you can charge more when that peak comes. Or you can have real time pricing. So this is coming up to be, a major reform will be required to enable real time pricing, in which, based on how the wholesale power market prices are, we can charge a real time pricing across. So it will be based hourly prices. So you won't have flat retail price. It can vary with respect to time. So we'll discuss more in the coming weeks. So this is all that I wanted to discuss today. So I discussed quite a lot of things. Since no one is present in this meeting, it's illogical for me to summarize everything. You can always go back and check if you didn't get anything. But we discussed a lot of things today. We started with optimal PMU placement, then we moved on to cyber attacks, right? How cyber physical systems have come into being, how cyber attacks are manipulating these systems. Then we talked about virtual inertia, why that is important. Then we moved on to demand side management, because it is a form of a virtual inertia which can help you maintain frequency imbalance. And then we discussed how distribution utilities are very stressed. And then we discussed how demand side management can be programmed using an optimization problem. And then we discussed demand response. So let's move on with questions. Since no one is present, I'll just answer this on my own. So I just want to reiterate that please join the sessions. I mean, I'll assure you, if you have followed the lectures for the 5 lecture videos that the instructor has uploaded, if you have followed them, if you come to this lecture now, you'll get everything. But if you don't go through them before coming to this lecture, you won't get anything, because what I do is I don't teach you for 5 hours, right? I teach you for 2 hours. So I can't cover 5 hours of, this lecture material in just 2 hours. It's unfair and difficult for me. So it's up to you. I mean, if you love watching this on YouTube, do give it a like. I mean, I'll appreciate it. But anyways, it's fine for me. So which one of the following is not a type of classical optimization technique? So a linear programming is a type of a classical optimization technique in which the objective function as well as the constraints are linear. In mixed integer linear programming, what happens is your objective functions and constraints are linear in nature, but there are some binary variables as well, apart from the continuous variables. So it is a form of classical optimization technique. In binary search, what you do is, so just like a binary search in your uh, searching a number in array, right? Same thing happens here as well. What you do is, so so how do you do it? So what you want to do is, you want to find when the minimization happens, right? When that, so let's say this is how your optimization function looks like, right? I should draw it like this. This is how your objective function looks like. So you want to find minimum, right? So let's say you are at here and here. What you do is, you check if let's say, so binary search, what it does is, you get an index of the highest number and the lowest number. So what I want is x1 and x2. Based on that, you find a midpoint, which is x1 plus x2 by 2. You get a midpoint like this. Then you check if this midpoint is less than or greater than target. So let's say this is less than the target, right? So what you do is, you then shift your you then shift. How do you shift it? Then you create a new midpoint. Your midpoint now becomes x3 plus x2 by 2. So based on that, by checking with respect to a target, based on checking with respect to a target, you come to a minimum point. So this is called binary search method, and this is heuristic based. This is not classical optimization, because you're not solving it using mathematics. What you're doing is, you are initializing two variables and you're just finding a midpoint, and based on that you are trying to find a common ground. So this is not a classical optimization technique. So, but a non-linear programming in which your objective function and constraints can be non-linear, it is a classical optimization technique. Next, second question. The lowest minimum number of PMUs to enable full observability of IEEE bus 30 transmission system. So in first lecture, if you go through the reference number 1, you'll find the answer, and the answer is 7. And this is tried and tested method. In earlier references, if you find optimal PMU placement, I did not get the reference, but there is one paper in IEEE transaction on power systems by Saika Chakrabarti, who is a teacher here. Sorry, who is a teacher here, and he has come up with this. optimal PMU placement problem, in which he has found for an IEEE 30 bus system, the lowest number is 7. Next, which one of the methods is exclusively and only a distribution detection approach? So the correct answer is not chi-square, not state estimation, not even binary hypothesis, right? So I've already given you this table. So in distributed, only centralized methods after approximation, singular value decomposition, and and observer based method like fault detection and identification come. So the correct answer to this question is observer based. Moving on, which demand side management strategy is more reliable compared to other strategies? So load growth. So can you can you rely on growing the load? Why do you can't, right? It's a thing that happens on its own. The load will grow, but it you can't instill a growth on it, immediately. So this is not a reliable method. Then flexible load. So since it's flexible, you can ask the customer who has this flexible load to to shift its usage, but it's up to him, right? You cannot order him to shift the load, right? So it's not reliable. Load shifting also is not reliable. The only thing is peak clipping. So what you do is you enable a power cut. When a peak happens, cut down the power. So it's the most reliable, right? Because you will get the thing that you wanted out of it, right? You're getting uh yeah, you're getting what you wanted out of it. So the correct answer is peak clipping. Yeah. Mm. When I say reliably, right, it's reliable. I mean, the most reliable is this only. Shifting may or may not happen. Flexible load may or may not be flexible. Load growth is not at all reliable. As peak clipping, you are just cutting down the power. It's the most reliable. Which one of the below mentioned DSM strategies refers to the load shedding events? Peak clipping. In peak clipping, you shed the load. You cut down power supply to the load, and your load is now clipped. Sixth, energy management strategies and DC microgrid aim to. So, increase the stress on the energy storage system? No, you don't want to increase the stress on the system, any system, right? Reduce the peak energy deficit? Yes, it can reduce the peak energy deficit. Degrade the lifespan of the energy storage? No, that is not what you want to do. Extract maximum power from PV and bit. It's subject to constraints, right? You may not always want to extract maximum power. So the correct answer is reduce the peak energy deficit. So you want to reduce the peak energy deficit. That is why for a DC microgrid, you aim to have energy management strategies. 7. The critical difference between demand side management and demand responses. Right. So DSM is performed at the utility level and DR is performed at both utility and consumer level. So the correct answer is A. I've told you in the beginning, DSM, utility asks you to do. DR, utility can ask, it's up to user if it wants to do or not. Which of the following is not an objective of demand response? Minimize the electricity cost, minimizing the aggregated power consumption. This is an objective. Maximizing, so you want to minimize the electricity cost, right? Because you're clipping peak, you are in short minimizing the electricity cost as well. What is not an objective is maximizing the energy cost. Why would you want to maximize the energy cost, right? So this is not an objective. Ninth, which of the following holds the responsibility to provide the reference AC bus voltage and frequency in an islanded AC microgrid? This was discussed last time, and the correct answer is diesel generator, because you can control the output in such a way that it can constantly provide and hold power at that point, and it can also provide inertia. Loads, battery, and PV are not used if you have an islanded microgrid with battery, diesel generator, PV, and loads. Right. So 10th, a diesel generator is capable of dash injecting active power only, injecting active power at the cost of absorbing reactive power always, absorbing reactive power only, injecting both active and reactive power. So the correct answer is D, injecting both active and reactive power. So in diesel generator, you have a generator, right? You can control active power by using generator governor control, and you can control reactive power because you're using reactive power to generate power, right? It's a rotating mass which relies on uh, magnetism, right? The effect of EMF, electromagnetic force. So by controlling the excitation system. By controlling the exciter, you can control the amount of reactive power coming in and out of the system. 11th, which is not an objective of demand side management. Peak reduction, optimal scheduling of generation resources. This is an objective. You don't want to schedule generation resources. That is not up to you. But yeah, if they are present at the distribution side, you can control. If you have generating resources at the distribution side, you can control or schedule them. Delaying the penetration of renewable energy resources. So you don't, this is not an objective, right? Why would you want to delay the penetration of renewable energy resources? So the correct answer is C. 12th, the wind turbine output power is processed through dash to feed the power to the standalone DC microgrid. So you have DC, so you have DC output because it's a DC microgrid, and you have AC output from the okay, I'll write DC microgrid, and you have output from turbine is DC, sorry, AC, right? So what you do, you convert it first to DC, and then you use a DC to DC converter to convert it to a suitable form of DC that is required to keep the bus voltage at a particular level, right? So you require AC to DC and then DC to DC conversion. So the correct answer is A. So you first convert AC to DC and then you convert DC to DC again. Next, DCOPF is used for optimal power for studies of dash network. So even though the name calls DCOPF, it's not, sorry, it's not first, it's 13th. It's not DCOPF, it's direct current approximation. It's not like you are only utilizing it for direct current because it has this BIJ term, right? What is BIJ? It's susceptance, which is nothing but 1 upon Xij, right? And reactances are only present in AC networks. So the correct answer is AC. So it's only applicable to AC. What are the disadvantages of cyber physical systems? So you have cyber attacks, you can have network congestion, and you can have malicious control effects. So the correct answer is all of the above. Which of the following is an indication of real-time balance between supply and demand? So as I told you, if there is an imbalance between generation and load, your frequency varies. So the correct answer is A. Next, inertia and with respect to frequency and essential reliability support service, map the following. So inertia, so the response time is in order of cycles, that's true. So you can get within a few cycles, this kicks in, right? Order of seconds, no. Then you have response time in order of minutes, no. Synchronous machine. So inertia is only applicable to synchronous machines. For significant communication infrastructure, you don't want. Then for two, you have primary frequency response. So you have two. This is not you in order of seconds. It's in order of seconds, not in minutes. So primary frequency response. So it can be for anyone, right? Controlling droop for any. You can control it for non-synchronous generators too. Significant communication infrastructure. No, you don't require communication because it's automatic. Automatically the output is controlled. Next, you have secondary frequency response. So secondary frequency response is the order, just a second. Okay. So secondary frequency response. So you have three, and what you want, just a second. Okay. I'm correct. So secondary frequency response, no, the order of is not in seconds, and it's in minutes. So the response kicks in within a few minutes. So it's three. Is it for synchronous machine only? No. Does it require significant communication infrastructure? Yes, because now you have to issue AGC commands to the respective generators. So the correct answer is this. So correct answer is 114, 114. It's either this or this. Then 22, 22, and 3, 35. Oh, sorry, 35. So right. So the correct answer is this. B. Which of the following statements is correct? PV array provides inertia and active power control support. No. PV array provides inertia but not, this is also wrong. PV array provides active power support but not inertia, neither. So the correct answer is 3. Only third statement is true. What are the different demand side management strategies? Peak reduction, flexible load, load growth. So the all of the above is the correct answer. Dash is a type of dynamic pricing based DR strategy. Time of use, incentive, time of use and incentive. So incentive is not a dynamic pricing based strategy. So the correct answer is time of use. Right? Hmm. Which sector has the highest load demand share in Indian power sector? So this is a controversial question. So few years back, if the data they have taken to answer this question, if I take a look at this graph, so few years back, industrial load was less than residential load, right? But now it has increased. It has increased by a very big margin. So the correct answer right now with the current data that I've gotten. So this is for the current data for 24 to 25. You can check this website. It's a very cool website. You can get a lot of information from it. So this website link I've already given. Go feel free and check whatever graphs they have. You'll see that industrial load is more. Next, which of the following has the highest and second highest share of installed power capacity at the end of 2017 in India? So the 2017 is a very, it's old data. So the correct answer is coal and hydro. And I think it's still coal and hydro, but you have to check. But I feel it's still coal and hydro. So the correct answer is coal and hydro. Right. So we discussed a lot of things, you see. And what I want from you is, sorry. Hmm. What I want from you is to go through this lecture, and if you have any doubts at all, feel free to, write it in the comment section, and I will be more than happy to answer them. And I would request you to please, you know, uh, watch these lectures if you want. I mean, if you're not getting anything, please ask your doubts. I am very, um, I, I'm eager to solve your doubts as well. And uh, yeah, thank you. Thank you for watching this on YouTube, and I'll see you all in the next class, hopefully. Bye.